Welcome to the October 2025 GoldSim webinar on practical techniques for efficient and robust simulation. Today's presentation is mostly going to be a little bit of this and a little bit of that, talking about ideas that I have for helping you when you're dealing with a big model. And this is one of those subjects where I'm not going to be able to cover everything in your particular case that you might have, but I'm hoping that a lot of my ideas will be useful in the long run for you. Mainly having to do with helping you with keeping a model organized, working as a team, also reducing the memory footprint of your model, and also increasing and improving the performance of the model. So those are the main things I'll be talking about. And so let's just get started. This model that we're looking at is a model that I've been involved with since 2006, actually. And I started working on this as it was a kind of a regional water supply and demand model for the Salt Lake Valley. This is an area in the state of Utah in the US. It's an arid region. There's a lot of population growth that's been going on there for a lot of years. And they were looking at the impact of reusing treated municipal wastewater, essentially, and treating it and using it for irrigation, and the impact that that would have on generally the downstream flows. It turned out that it kind of revealed some things about the system that were quite interesting, mainly that the irrigation for agriculture was going down and was projected to go down and has been since then, while municipal growth, the population growth is increasing. So there's a lot of residential, commercial growth going on and increasing while the agriculture is going down. And so that has a lot of implications on how much water gets diverted for these irrigation districts. So that was kind of a side thing, but a very important thing that came out of all of this. And I'm not really sure, I haven't really kept up since then what they've been doing. But over the years, I've helped researchers at the local university over there on continuing to build these models like this for this system. And so what we have here is a very complicated system, as you can see, and I'm zoomed in, so you don't even see the whole thing. If I zoom out, let me do that, then you'll see it's pretty pretty involved. And I would say this is kind of on the more complicated side of things of where we typically see GoldSim models, but they often get this way. And so it's important to have a couple things in mind when you're building these kinds of models. In this particular case, I'm using custom icons. And these are very simple icons. I made them so that there's like a flavor of an icon. It represents a certain type of thing in the real world. So like green represents agricultural irrigation, and these little blue things represent a diversion structure and stuff like that. Anyway, very basic. And I feel that drawing basic ones actually is pretty useful because why put a lot of detail in these kinds of icons, when you have so many of them, and they're just meant to give you a basic view of the whole system and like how to differentiate one versus another. Also, after a while, when you get so many influence lines like this, it makes you start to wonder, what's the point of the influence lines if there's so many of them, right? So you kind of have to be careful about that. And one of the ways to be more careful about the number of influence lines growing here is something that I talk about a lot in my webinars, and that is to separate out the information from the flow of the material or water that you're working with. And it's not always necessary to do that. But sometimes in the case like this one, it would help a lot because we really don't want to have too many lines in here. And so what I mean is, in a gold sim model, because of the way that you solve for flows in a gold sim model, you're doing it explicitly on an item by item basis. We're not doing a global flow optimization problem here. You can, but it would require building it from scratch, and that would be a whole different subject. But that's an important distinction to make here, because a flow optimization model, like if you look it up, max flow min cost network optimization, for example, it's a linear programming problem where you set up all of your demands and your supplies and your constraints in a matrix, and it solves it. We could do that kind of thing. But that's on the side. That's off to the side, built on your own, and then you'd have to link all the flows in. So that is something we can do, and I can show you an example if you're interested, where we rely on a Python script to solve for flows. But that's a kind of a specialized thing, and usually you can solve individual flows throughout a system, typically in your typical supply and demand model or mine water balance model or whatever kind of model we're building, where you have flows moving around to supply demands. So it could be that as long as your time step is small enough relative to your storage elements in your model, it usually works okay to do that. And what I mean by that is you just go around to each point and you say, okay, this diversion relies on information coming from this other place to determine how much water goes over to this thing over here, and et cetera. So you might say, okay, we have a demand at this node that I'm pointing to, and we need to supply it. Well, we have two places the water can come from. Let's just say there's a priority. So let's try to get everything we can from this supply. And then if there's anything left over, we'll just calculate whatever the shortage is still and go ask for that amount from the other place. But you can see here, we're starting to pass information around. We're saying, okay, we have we have a demand. We have to send the demand over to wherever this water's coming from. That's information that would move from one place to another, right? So what happens is when you do those kinds of things, when you ask for water from some other entity, you have to send information over there, and that's an influence line that would cause another line to be drawn in here. So there are ways, and I have other webinars I've talked about that specifically, in how to separate out requests like that from the actual flows that occur. And that is an important thing if you've got a very complex network like this, to think about those kinds of things. And I can point you into direction of like examples and other videos where we talk about that kind of thing if you're interested. By the way, at any point during this presentation, if you have questions, please do ask in the chat window. Also, I'll wait around to the end and you can ask anything. But another thing I wanted to talk about was when you double click on an influence line. So let's say we want to look at this node right here. This represents Salt Lake City, Utah, this little node right here. And this arrow pointing to it represents the water going there. And that's not the one I wanted to, it's not actually the one I wanted to show, but that's okay. Wait. Oh, yeah, I remember. It's up here. Okay, so let me open up the browser. Okay, so this model that we're looking at is inside this container called River Network. If I go in there, here's the whole model. And then if I come up one level, so I just went up, and so now all that's in there. And now at this level, we have like a higher level regional water supplies that are coming in. But in this level, let's say we click on this influence line, then what you see here is that we have 4 different pieces of information that are moving along this influence line. So this is something that's important, right? Because when you look at this without clicking on it, You don't know that, right? You just see, oh, there's something going from here over to here. What is it? Well, when you double click on it and you see this list, in a model that you're working on, this could be a mix of things. It could be different units. Some of the things could be water. Some of the things could be information. In the case of this one in particular, it is only water. They're just different. They're different flow streams going to different locations from the same source in this case. But what I wanted to point at was where they're going to, because in each case, on the from side, if you were familiar with the system, you would know, okay, pretty much what this, you could kind of decipher this a little bit. Maybe it's a little cryptic, but you could pretty much decipher what this is talking about if you were familiar with our abbreviations and things we're using in this model. It might require a glossary or something that's written up. But on this next side, on the to side, okay, so we know it's coming from this, in this case, it's the Salt Lake Aqueduct, and it's going to this unincorporated part of the city, is what that's saying. And then over here, we don't know. It just says total supply input number 3. Well, that's not very helpful for us. It's very generic. And so what you can do is what's helpful a lot of times is just to put in a reference, an expression element that just references something. And that's what's done here on this last one. This one used to say total supply dot input number 4, also was not helpful, but I changed it. So let's go look at that one. If I go in there, what you'll see is it's connected to this expression element, which is just taking that output, that same output. It's just referring to it. So this is often done. So let me just start over what the model used to do. What the model used to do was we had that output going directly into there. I'm not sure if everybody's following what I'm doing here exactly, but just know that all I did was I took the influence that's coming from over here. I'll double click on that again. And that's this one right here that I've highlighted in yellow. So the water supply is coming from here, and then it's going over to this location here, and it says input number 4. So like I said, it's not very helpful, but it does tell you a little bit more down here in the full path. If you look at the full path, then it tells you the container that it's in. So at least knowing the container would tell you, oh, okay, this is going into this container called SLC. I already know that's Salt Lake City. So, okay, now I get it. It's going over there to the Salt Lake City supply. So, looking at this kind of information can be helpful, but it's a little bit difficult on the to side right here. And then also if I go to, let's see, if I click here and I do an effects view, so I don't know if you knew that, but on any element, if you right click on the element, then you can select function of or effects to see what this thing is a function of or what it's affecting, right? So I want to say, what does it affect? And then now we just see a bunch of total supplies. Like, that is not as helpful, right? And so this is one of those things where in a big model, this can be a source of trouble for people trying to understand your larger model. And so it's this red one I know because I have versioning turned on, and I'll talk about versioning in a second. But I'll go there, and okay, so here we are. Now let me change this again so that we are instead of going directly from that source, I'll put in this expression element that I just called SLA distribution. It means distribution from Salt Lake Aqueduct. But anyway, and we should put that in the description as well. But anyway, so now we have the link going from that supply to this expression element, which all it does is just refer to something. So that's why I'm saying sometimes in a model, in a big model, especially like this, sometimes it's good to just have an expression element that does nothing else besides just refer to something. And you're just doing it to help with the naming and understanding so people know where things come and go. It's kind of like creating like a little portal that kind of helps just give users the people reading your model a little bit more context of what's happening. Okay, so now that we have that set up, if I go back and then if I double click on this, then we can see that we have this thing that says, oh, it's going to SLA distribution. Okay, so that makes more sense than just saying a generic total supply input number 4 there. So there are cases like that, just something to be aware of, and just keep those kinds of things in mind as you're building a model. That sometimes it's useful to do that kind of stuff. Okay, so generally speaking, with a big model like this, you'd probably be working with other people to build the model, and then it becomes critical to make sure to employ versioning. And in the latest version of GoldSim, now it's kind of a beefed up version of, or beefed up version of versioning, but the versioning system is a lot better now, because now what you can do is when you create a new version, it automatically saves a copy of its current state with a new version with the previous version number on it. Actually, on the new version that you created, it'll create a snapshot of that. So let's say you go through and you make a bunch of changes, and then you say, okay, let's create a new version to move on and do something else. It'll save off a copy of whatever state you had that in, so that you can keep going from that point forward. And it's just a nice way to, as you go along, to just kind of have a snapshot of where you were at that point. And then if you need to share it with somebody else, you can. And the nice thing is that if you check on the box, whatever version you check on, it will show you in the model in red all of the items that have changed since that version going forward, which is nice. So now if I go back and check the next version, then you'll see a lot of those red things went away, and it only shows the most recent changes that you've made. These are really important when you're working as a team with other people. Okay, so let's talk a little bit about, I was going to talk about time stepping, but we'll talk about that next. Right now, I want to talk about results and saving results. So if we look at the simulation settings, I just clicked on simulation settings right here. If we go to the simulation settings, then what we see here is that this model is running for a lot of days. It's actually going for many years with a 1-day time step, it says. So that is it's almost 13,000 time steps, 12,785 time steps, as you see down here. So this is an area down here you kind of want to just make sure you check every now and then. If this number starts getting too big, that could be problematic. Once it gets up in the gigabytes range, then it's starting to, become problematic, because it won't be too many more steps. Like if you decided to add more realizations or add some sort of dimension to it, maybe add more time steps or change your time step, all of a sudden you'll be running into a situation where your operating system would not be able to handle a run. And then you're kind of like, you risk crashing the application if you exceed that. So we try to do everything we can to prevent users from going there, but it's not possible for us to prevent it because of just all the flexibility that we provide in the number of time steps that you're evaluating. But so just a couple of things I just wanted to mention about that. So the first thing is just, keep in mind what you see down here, and just be aware of it. You can also click on the show scheduled updates button right here to just get an overview of what the model will be saving and when. So the capital H means time history points. Those are all of your time history charts. Those are the points at which it will show values for there as you go along. And then you can also see when the reporting periods will be shown. And so that can be useful. And then also there's a difference between what it's saving and what it's computing. So the basic step is what it will compute. It will also compute, update all of your elements, not only on these basic steps, but it will also do it on unscheduled steps as well. And so we can determine whether or not we're allowing unscheduled steps by going to the advanced settings, which is this button down here. If I click on that, then what you see in this particular model, we are not allowing unscheduled updates. we say it's recommended. It is the default to allow them. And in my opinion, we should allow them. Now, I might argue that sometimes we can do things in the model to prevent them if we want to. But a lot of times they're useful, sometimes they're necessary. And an example is a reservoir, a large, maybe a small reservoir, when it dries up, when it goes empty, it's not going to land exactly on a scheduled update when it becomes empty. Now, so that would insert an unscheduled step. We'll talk more about that in a little bit. But if you uncheck it, then what it does is it just says, well, if we're approaching empty at a reservoir, then we'll just say there's an average over the full time step of discharge to make it empty by the end of the scheduled step, for example. So it's kind of like the way you would build a model in a spreadsheet. Most hydrological models do this kind of thing, where they don't allow unscheduled updates. But because GoldSim is a dynamic simulator, it really should be including these. But I just want to make sure that you're aware of that. This is where a lot of people get hung up here, is that they are allowing unscheduled steps and they don't realize that a lot of them are occurring. And we have to, there's information that has to be saved for those. And so that increases the runtime, for example. So your performance could be impacted with a lot of those. So just be aware of this option. But I want you to understand how to deal with unscheduled steps, which I'll talk about next. But before I go there, let's talk more about saving information and history about your model. If you go to the information tab of the simulation settings, you'll see that it shows you more information about things. The number of outputs is important because that is going to affect how much information it needs to save. And you could have a lot of non-scalar outputs, matrix or vectors, and that would definitely increase that number a lot. So anyway, you can look at through all of the rest of these memory being used and stuff. It just depends on the type of model that you have, what these can be. But you just want to be aware of them and make sure that you're not getting a number that's beyond what your operating system can handle with all your other applications that are running, for example. So one of the things we've provided ways in your model to kind of to reduce that memory footprint. So let's say you have a container with a lot of stuff going on, and that would be this case with this river network. What you can do here is you can double click on it, and then down at the bottom it says save enable results. We can temporarily or permanently, you can disable time history results elements. Let's say you've thrown a whole bunch of them in there over time, they've built up, and maybe you only need to look at a couple of them, right? So then you could check this to disable them. And then you can also go to the information tab, and you can be a little more aggressive here. And we can say, actually, for all of the elements in this container, I don't want to save any time histories for any of the elements inside of there. Because what you can do is you can say, just pick and choose the ones that you want and connect them to a time history result element. So what I mean by that is you can go in here and you could say, I have this time history results right here. And all I need in this time history result is to look at reach number 11 and I don't know, the total outdoor return flow from this one city for some reason. And, or, you just pick a few things that you need for sure to show in a report or something like that. And then that's all you need. And if that's the case, then you could come back to the container and say, okay, everything else, we don't need it. And so I can just turn off all time histories. And then all of a sudden, boom, this has gone down from whatever this was, 64 megabytes. Now it's down to 1. But that's kind of a big sweeping change that you cannot just recursively just change back. And when I say recursively, what this did is when I clicked on this, it recursively goes through all the subcontainers inside of this container and turns off all the results. Now, it doesn't mean that it's not being calculated anymore. It's not that. Everything's being calculated still. But it's not saving the results anymore as it goes along. It still has to do all the same calculations. I just want to make sure that's clear. But you can see now it's not it doesn't have to have the memory to save all of that time history information because I just removed it. The only time you'd really care about turning off final values is if you could have a model with a very large amount of outputs due to matrices, very large matrices. And in some of those cases, you'd want to turn off final values. Okay, but then you might ask, well, what if I want to turn all those back on? Well, you'd have to go to a previous version of your model, but to turn those back on now, I'm gonna have to go into individual. I'm gonna have to go to each individual element, and you can see here it's turned off, and that's because I forced it off with that button. I'd have to go to each one individually and turn them back on, which is probably not something you want to do. But we did this in a way to it's too difficult for us to enable the thing to make it turn everything back on automatically. But it was more straightforward for us to allow you to turn it off. Plus, we're trying to get everybody to reduce the amount and then only save what they need. Especially with big models, that's important. Okay, so let's talk about performance of the model. And I'm going to go to a very simple model now, and this is just a simple reservoir that we're modeling. And what it has in here is, let's say, this flood level of 100 cubic meters. This is a level that we've set. It's like a policy, and we say anything above that number. I mean, we don't want the reservoir to ever go above that number. Essentially, is what we're saying. So initially, a very simple model, what we could do is we could say, let's just make that the upper bound. So we can come over here and we could just say, let's make that flood level the upper bound. And then it will never go above that. It'll force it to never go above that point. And I'm going to disable this interrupt element first. We don't need that for now. Okay, so now I have a pool that has some sort of inflow, and then it has this flood level, we're calling it, that just is the upper bound. It will never go above. So if I run this model, then if I look at the history, so then what we see here, oh, and I forgot. I was working on this in the previous session, and I forgot. Okay. And we're probably going to get a warning because now I have an overflow. Yeah. So when I run the model now, I get this warning down here. It says the pool element is overflowing, but there's nothing linked to the overflow output. And that was just a precaution that we provide because some users they had overflows in their water balance model, but they weren't going anywhere. And that could be a problem. That would be a mass balance problem. So we wanted to issue that warning. If you're not connecting your overflow to anything, which I'm not right now. So I have this overflow. I could even plot it right here. I have this overflow occurring and I'm not sending it anywhere. So that's why the warning happened. But anyway, when I look at this plot, so what it shows here is that the pool goes up and it hits 100, shown over here on the Y2 axis. It hits 100 and then it just immediately just stops. And then overflow is occurring. And I know I said pool 1 overflow down there. That's the wrong one. Let me change that to, okay. So, so this is the full picture. So the overflow occurs when we hit the upper bound like that. But the one thing to keep in mind now is that we've inserted an unscheduled step right when the overflow starts to occur. So you can see when the pool hits that top upper bound, we insert a time step. So this is not a big deal. However, you could have some logic in here that says something like, when you approach the upper bound or hit the upper bound, we need to turn some sort of flow on to remove that water. So we could come in here and say, okay, if the pool is ever greater than or equal to that flood level, then we want to discharge some amount. And so now we can add that as and I'll call this flood. I don't want to call it overflow because we already have an overflow. Flood flow. Okay, so that will be another outflow called flood flow. I have another loss in here. This is like, you could consider this like evaporation or something. We'll call it that. Evaporation. So I have evaporation rate, which is just a function of its own volume. And then I have this overflow. And so then I run this and we see that this is not doing anything because we have that upper bound. We have that upper bound in there. But it does appear that something strange is happening, right? So I'm not seeing this overflow occur, but I'm still noticing, well, a couple of things. The reservoir volume is not going over 100, but it's also doing the sawtooth thing. And so we have high resolution histories. Okay, I need to back up a little bit more because there's a few things going on here. So let's go to the simulation settings and look at this. I'm running this model for 100 days. I have a 1-day time step. And then if I go to the advanced here, you can see I am allowing unscheduled updates. And I have checked this box that says include unscheduled updates in time histories. So that's really important. This is a good debugging step to take. I don't think you need to have this box here checked all the time. But it's really good to have it when you're trying to figure out what's going on in your model and debugging it. You definitely want this checked because it shows you everything, not only the values at the 1-day time steps, which is what I'm defining here. See, if I go to the show scheduled updates, see it. This is what it's pre-programmed to show you. It's pre-programmed before we run the model. It's pre-programmed to show you all the values at all these time points. However, it's not pre-programmed to show you anything at unscheduled steps because it doesn't know when those will occur. But if you check this box, then it will force the time history elements to show you what did occur during those unscheduled events. So I'm going to add to this chart, and in addition to the overflow, I'm going to add also that flood flow thing that we added. So I'll run that. Okay, so now we can see we don't have any overflows because this flood flow has taken over and it said, oh, as soon as we hit the upper bound, we need to discharge. And so it's doing that sawtooth thing. And then you come in here and you see that, okay, now it's like, it's oscillating. You see it's 50 here for a little while for only less than it's like 0.13 days. It's 50 and then it turns off. And then it turns on again and it's 50 for about 0.7 days and then off and etc. So that still, it doesn't seem like that many inserted steps, but this can really add up in your model, especially because once that time step is inserted right here, your whole model updates. Your whole model updates unless you have another container that has a different clock. Okay, so that's a different thing. But typically, this would cause your whole entire model, all the elements in your whole model will be updating on this time step and on this one and on this one. And so imagine you have many reservoirs and they all have this situation where you're inserting these unscheduled events at all these different places and you start adding more and more time steps and more things start to happen. So what I mean by that is that if I shorten the time step, if I shorten it to, let's say, 1 hour and run it and look at the results, what you see is that we have a different result. And we don't want that typically. You don't really want to have different behavior just because you changed the time step. I mean, it's okay in some cases, but what I've learned over the years is that that's typically not something you want to do. You don't want to have your model operate differently just because you changed the time step. It should be immune to that for the most part. And in this case, this model is definitely not. Okay, so let's change this back to 1 day. And let's take a look at maybe fixing this a little bit. But before I do that, so I'm running this with a 1 day time step, and now we just have a few inserted steps here. 1, 2, 3, 4, 5, 6 or so inserted time steps here. That's not a big deal. But because it's inserting these steps, we see a lot of models where people are referring to a run property called time step length. And the run property, when I say run property, you can see all of our GoldSim run properties if you go over here to the browser and then just right click anywhere in the browser and select this show elements sub items. And then you'll see this local properties folder. These are our run properties. So these are really important for a dynamic simulation platform like GoldSim. And in GoldSim, we have this one called time step length right here. And this is often confused to be the length of time between your scheduled updates. In our case, 24 hours, but this is not the case. So this is actually the amount of time since the last update. So if we were to look again at this time history in a table view, and we go here to this first unscheduled update, then the time step length value at this moment in time right here will be 0.869 approximately days. So that's really important. So what we see a lot is people, when they're building these big models, they might calculate a flow rate that's based on a volume or a quantity of some sort. And here's a case. Let's say we're calculating this flow. I don't know what this is. Let's call it some sort of demand, or who knows what it is. But it's some sort of flow rate that is being calculated. And let's say they're doing that based on a volume that they know that they can access, let's say this volume, and then divide it by this time step length. So if you do that and you have unscheduled steps, then let's see what the result is. I'll just print it. So what happens is there was a moment in there where the time step length became very small. And then you divide a number by a very small number and you get a very big number. And so what was probably intended here, most of the time, what's intended is not that, but instead doing something like this, where you say the volume divided by a constant. So I do this a lot of times because there's just cases where you need to do an approximation. It may not be realistic necessarily. And 1 second, I need to adjust my status on my Teams because I'm getting way too many. Change this to do not disturb. Okay. Okay. So a lot of times this kind of calculation is necessary for kind of an approximation. I would say it's maybe not in the real world what is used to define or control a flow or something. It might actually be a hydraulics or a valve or something, but we might be doing some sort of conceptual thing. And in that kind of a case, what I would do is I would create a data element here, and I call this like DT for delta time or something like that. And then I'll just put it's 1 day or whatever my basic time step is, right? I'll put that in, and then make that global. Put this at the root level of your model, like a global constant. And then anywhere that you're trying to calculate that, then you just put that there. That's definitely far and away the best way to do it, because let's compare these two outputs. So here's the flow with using the 1 day time step, and then if I add the one that uses the time step length, then that's the difference. And so this is common. We see users doing this, making this mistake, and it causes an artificial spike that not only is unexpected, but also might not even be noticed, because it might happen during an unscheduled step And if you don't have the unscheduled steps turned on in your results, then you might not even notice it. And then all of a sudden you'll see, you know, some impact from that, like a sudden drop or sudden rise in your, you know, pond level somewhere, totally unexpected. So that's something to keep in mind there and watch out for. But beyond that, what we really want to do is avoid equations like this, where we say, okay, if the pool is greater than this number, then it's this flow, otherwise it's not. I mean, this makes sense in a discrete model, in a discrete event model, like a spreadsheet. It makes sense more because we're just talking about discrete quantities, but in GoldSim, we're talking about flows that occur during a duration that's integrated over time. So we cannot really get away with these kinds of equations because it can impact the time stepping and the overall behavior of your model. So where you want to go from that is instead use a controller, a flow controller, or something similar. And a flow controller, what it will do is it acts like a valve or a pump, a variable speed pump, or a constant speed pump, or anything that can control flow. And so what this does is, if I double click on it, then what we can do here is, oh, and I can't remember if I showed you what happens. Let me go back to going to 1 hour time step. 1 hour time step. Then what you see is with this if statement, is that you get oscillations that are happening so rapidly, it's like a solid blob of color. And so that's because we've just shortened the time step and it's reacting a lot faster. And so we want to be careful of getting into those situations. And so what we can do is instead, we can use a controller that says, okay, let's put a little buffer in there. We don't need to turn it on and off at exactly 100. We can have a little bit of a buffer. So let's go ahead and say we're going to define a target, and our target is the flood level. Okay, and then we'll just say, we'll give or take, let's say 5 cubic meters. So the flood level is 100, and we're going to allow it to float above and below that target by 5 cubic meters. And I'll show you what that means when we run this. So I'm going to now go in the reservoir, or in the pool, and I'm going to replace this flood flow with the controller. And then I'm going to remove this upper bound. Well, we could put an upper bound in, but let's make it higher. Let's make it 150 cubic meters. Whoops. This is the kind of thing I like to do, and sometimes I won't even put an upper bound because really I don't want to ever be there. To me, that would be an error in the model. In most cases, I realize that sometimes for a simplistic view, upper bound is just fine. It works just fine in some cases. But in a lot of cases, you don't necessarily want it to be so constrained exactly to that number, especially if it represents a flood level or, you know, some sort of policy or maybe a spillway or, you know, something like that, where it's not a hard and fast like number that it never goes above. It's actually can go a little above it. But this number, in my opinion, upper bound would be something more like catastrophic, like the top of the dam or something, you know, where you never want to get it up to that point. And if it is, then you want to put in an interrupt element that says, hey, they hit that upper bound. This is terrible. Let's not do that. So instead, I'm going to control the flood flow with this controller. So let's see what this looks like. Okay, so we have 1 hour time steps. It's not quite as it's not happening quite as fast. It is still kind of going up and down pretty rapidly, and you can see it's doing that within a day, between days. This is a whole day right here that's gone by, and it's already oscillated 3 or 4 times between. So then all that means we need to do, we don't need to adjust the time step. We can just come in here and say, let's just make the deadband bigger. Let's make it 10. So then, and then we run that again. And now what we see is that we don't have as many oscillations happening. So now we have oscillations that are happening still within a period of a day. But if I make the time step even smaller, let's say I make the time step let's say I make it 10 minutes and run it. The nice thing is it does not change the behavior of the model. Not in the case of this control right here. We still have the same number of ups and downs. That didn't change at all. So that's something that's really nice. And it doesn't cause, like, because I'm using this, we don't have an unexpected hit on the performance of our model in this case. So I wanted to bring this up because of how common it is that we see this kind of thing. Now, if you don't like this type of approach for this type of control using this deadband, because this does insert time steps, by the way, what we can do is use a proportional controller instead. I'm going to change this back to 1 day time steps. So we can use a proportional control, and the proportional control throttles it down. Instead of just turning it on and off, it does more of a throttling. So now let me go to proportional, and then I'm just going to put in a little bit of it's called bias. And you can read about this in our help documentation, but I'm just putting in some tuning factors here. And okay, let's see how that goes. Okay, so now you can see what it's doing is it probably needs to be a higher capacity, but it's limited to this capacity. But what it does is it turns on when we hit 100. That's our target, or that's our kind of our flood point, but it still allows it to rise. It's just on constant. It's like it's taking everything out of that it possibly can because we're above the 100 level. And then as soon as we drop below the 100, then it turns off. But if we increase the capacity in this controller, let's say it's 150 instead of just 50. Oh, wait, it still shows 50. Oh. I need to think about this for a second, what I'm doing. I think one of my problems is I need to make sure the names are okay. I think there was a little bit of confusion with what these various names were doing. Okay, there we go. Oh, the names are still a little bit not very helpful. Okay, here we go. Flood flow, overflow. There we go. Okay, so now we see that the overflow is adjusting as it moves through time, and it adjusts based on how far away we are from that target level of 100. So over on the right side of this axis, you see that we rise up above 100, and the higher we are above 100, the more that this increases accordingly. So this would be kind of like similar to what you would do with a rating curve, for example, to conceptually model maybe more complex hydraulics. You could do it conceptually with a controller in a way that does not add a lot of inserted, actually it doesn't add any inserted time steps. We have an inserted time step here at 120. And I'm trying to remember why we have that unscheduled event there. But anyway, we're not inserting a whole bunch of inserted steps that will, hurt the performance of this model over time here. Okay, so I hope that makes sense. It's an important concept when you're dealing with modeling outflows from a pool or a reservoir element. The other thing I wanted to mention is that it could be that you want smaller time steps, but only during certain times. So instead of just saying, okay, I'm going in here and I want to make the whole model run for 1 hour time steps, instead you could say, actually, I only want 1 hour time steps when the model is above the flood level, let's say. And so this is one every day. Okay. So what we can do is put an expression element in here that says we'll make this be a condition, and then we can say if, or no, we don't even need to say if. We just need to say pool 1 is greater than the flood level. When that's true, then we're going to be smaller steps on. So when this becomes true, we want smaller time steps. So to do that, you go to the simulation settings and then go to advanced. And then right here, say dynamically control the time between updates. So we could say if smaller time steps on, then 1 hour, otherwise 1 day. And then run the model. And then look at the table. And now you can see that these are hour time steps just during that period. In this area right here, and then there might be a couple over here. So that would be a way to increase the precision for just in certain conditions. There could also be times where only in one container do you want to have increased time steps. So in a container, you can double click on the container and change the internal clock. And then in the internal clock tab, you could say, I want this to be 1 hour. Oh, whoops. I want this to be 1 hour. And then everything inside of here will have 1 hour time steps. The only thing is that you can't really do that for things that are impacting things that are outside. So I couldn't really say, oh, I want this controller to be in here and I want it to have 1 hour time steps and everything out here. Well, you could in this case, but in some other cases, you have a certain type of feedback between two things that you are not able to, separate it out like that. But in some cases, you can. So it just depends on the feedback that's going back and forth. But that could be a way to compartmentalize the model and have higher precision in time in only one location and not another. And then the last thing I wanted to say before ending is that one big drag on performance of a model is working with external files. So if you're interacting with Microsoft Excel, which is really easy to do in GoldSim, just keep in mind that that does take a lot of time to do that. So one thing you can do is to avoid, taking a lot of time every single time you run the model. If you are exporting your results to Excel, for example, one thing you can do here is in the model options, you can go here to the results tab and then just choose this do not export results. And then that way you can then just click this button when you want to export them, not do it every time, because that can take a lot of time every time you run it, because it has to start up Excel, in the background and then write to the file, and it's even slower than writing to a text file. So I would say, and until you need it to export every time you run it, I would say, turn this off, and then you can just click the button when you want it to export. You can also add a dashboard or add a button to a dashboard like this, in this dashboard, if I click on the properties of this button, you can see that it exports the simulation results. So then you could have your end users, click this when they're ready to export the results after they run the model, just when they choose to do it, instead of making the model do it every time. There are some expensive functions in GoldSim. One thing that is pretty expensive to do is to do a lookup in a time series. So let's say you have a time series that's very, very large. And if you were to do a function on this time series that looks something like this, time series, and then, I don't know, some day that might be dynamic. Let's say that's a changing, it doesn't have to, not a constant 4 days, but something that might be moving all over the place. That's kind of doing like a lookup on a really big time series. That's pretty expensive to do that. Also doing lookups on a really large vector or data element or matrix. We have increased and improved the performance of a lot of those kinds of things, but they're still relatively, they're kind of expensive to do. A lookup table might be faster, actually, a little bit faster to do that lookup. It just kind of depends on the situation, but those are some things that could take a while. But I would say that the biggest, far and above all the others, is going to be when you have your own custom looping, and that would happen in a script element. So a script element is a way for you to write your own for loops, for example. So you could have some sort of variable here that's counting something, I equals 0, and then you have a for loop here that says when counter is less than, some big number like this, and then you do some sort of iteration. If you don't put in like a break statement or some way to get out of the for loop, and you accidentally, you might not realize it, but this for loop is like updating way more times than you want it to, or it might be continuing on much further than you want it to. That can definitely add a lot of performance overhead to your model and increase the runtime quite a bit. Another one, culprit, is a lookup table, or a looping container. So the container can have a looping capability, and you could have it loop until some convergence happens. Those kinds of things can eat up a lot as well. So our time is up, but I'm happy to wait around here for a bit if you have any questions. I know I kind of went on to a lot of topics here, but these are some of the things that we see that are potentially causing some performance issues with big models. So I hope that was useful. Thank you for joining, and I hope to see you next month. And like I said, I will be waiting here a little bit to answer any further questions that you might have.